Thanks everybody for this for attending this webinar. I'm going to try to summarize the project that we are running now, that is essentially designing and manufacturing a CubeSat for atmospheric together with radio astronomy applications. This is a regional consortium in the Madrid region in Spain, already funded with 1.2 million euros for designing a CubeSat that is called Martin Lara, as you are going to see later at the end. Essentially, the main goal of the CubeSat from the scientific point of view, together with the technological point of view, is designing a new paradigm in radiometer technology that it is essentially we are not going to use any kind of cryogenic system for cooling down the radiometer and reaching a good sensitivity. Let me see if it works. Yes, it works. So essentially, and I'm going to summarize this a little bit. Just from the radio astronomy point of view, there are a few bands in the millimeter and submillimeter wavelengths where the sky is really interesting for astronomers and for radio astronomers. And also, there are a few bands where it's quite interesting from the atmospheric point of view. In the consortium, there are two companies engaged, that is Cener and Airbus. Both of them are, well, Cener is designing the platform together with our aerospace engineer, and Airbus is going to be one of the scientific partners for the mission. Essentially, they are interested in the atmospheric bands for climate weather changing. And so we have another scientific partner that is the Complutense University, where they would like to see to the South Pole for checking particles that are magnetic charged due to the sun wind. So essentially, the technology that we propose is a new radiometer concept, based where our main focus interest is avoiding the cryogenic system. Essentially, all the cryogenic operations based on bolometer, superconductor, kinetic inductance detectors, or high electron bolometers are based on cryogenic system, and if not, they can work under room temperature, but the minimum or the opposite, the maximum sensitivity that they can reach is roughly 4.5 times the quantum noise predicted by, for example, Colorado University or National Radio Astronomy Observatory. Both institutions are collaborating with us. So the concept that we propose is this one. This should be a video, but we tried just that it doesn't work, so I'm going to put this slide. Essentially, what we are using is a totally passive system based on a non-linear crystal device that is typically lithium niobate or lithium tantalate, where we pump with a local oscillator in optics, and also we match the radio frequency signal that we would like to detect. Both signals are bit in the non-linear crystal, that is this blue spot that you have there, and we make an up conversion process passive. All the time is passive, so we don't consume any kind of power, and we make an up conversion process to the optic domain. So the radio frequency signal from the electrical engineering point of view is modulating a carrier in the optic domain. I'm going to show you. This is the kind of resonator that we are using. I insist they are lithium niobate or lithium tantalate. We are trying to use another material, but this works really well, as you are going to see in our first proof of concept labs. This is again a video that doesn't work. I'm going to show you here the scheme. So essentially, on the left, on the top left, you have the crystal. just below the prism. So essentially, you have a waveguide where we couple with the antenna a radio frequency signal. We have the crystal, a lithium niobate, where we couple the optic signal, and in that circle that is semi-transparent to our eye is where the signals are bit, and the upconversion process is successful, so we can detect the radio frequency signal as a small modulation in the optic domain. Sorry. So here you have several experiments that I don't want to bore to you. Essentially, the good point, and this is what I would like that you see, is this plot. The good point of this new approach is that we are able to get an extremely effective, low effective noise temperature, reaching, for example, lower temperatures than 10 Kelvin. Have a look to the blue line, that is the resonator on the top. So we have a small piece of lithium niobate with a high Q, and there, without any kind of cryogenic system, we are able to touch almost 10 Kelvin of effective noise temperature of the complete system, for sure. I'm going to show you now some results of our experiments. If you have doubts, for sure, I can tell you. So essentially, here is one of the measurements that we have. That peak that you have at roughly 194 terahertz is the carrier, the optic carrier, and just on the right you have the upconversion process. So not on the left, I insist, on the right. Obviously, we are generating two sidebands, and we are focusing only on the right hand. So there is where we are modulating with the microwave signal, the optic carrier, and we are detecting a signal at roughly 80 gigahertz with our radiometer. So this is a plot with an optic spectrum analyzer that shows that our concept is working. Sorry. Okay, here. I'm going to show you now some values about sensitivity. These are measurements again. So at 94 gigahertz, if we look, for example, to one of the state-of-the-art radiometers, that is the satellite WMAP, working at 85 Kelvin, in cycles, you have our sensitivity. So you can see how we can touch the same sensitivity as WMAP, working at 94 gigahertz, using two different geometries. With the one on the right in the plot, you can see that we are slightly above the sensitivity, but if we change the geometry of the resonator of this lithium niobate crystal, we are touching the sensitivity. And even we can increase that sensitivity more and more using another geometry as the one that we are now designing. This is another example of measurements of our sensitivity. In this time we are working at 180 gigahertz, and we are comparing with the sensitivity of low noise amplifiers working at room temperature of 300 Kelvin, and we are slightly below. Well, in other words, our sensitivity is slightly better than the low noise amplifiers for these radiometers based on low noise amplifiers. This is already published in Nature Photonics together with a scientific report in Nature that is published, I think, this month, probably. So as I told you in the very beginning of the talk, this is a project that is called Martin Lara, that is a millimeter wave array at room temperature for instruments in low altitude radio astronomy together with atmospheric observations. As I told you, Airbus and Complutense University of Madrid are interested in observation of the Earth. So we are designing the complete platform from scratch. We are a consortium from electrical engineering to aerospace engineering, and currently we are designing a 6-unit CubeSat where we are going to test this photonic or microwave photonic technology for this radiometer concept. We are going to try 3 frequencies. that is 140, 240, and 320 gigahertz. Sorry? Oh, okay. There is some noise. Sorry. The Martin Lara acronyms are related with these two kits, obviously. And these are the scientific goals that we have. And I'm going to show you now the antennas that we already have manufactured for the CubeSat. They are totally flat, as you can see, so we can attach the antennas strictly to the wall of the CubeSats without, well, the volume of the antennas is extremely low profile one. We are able to reach a directivity or a gain with these antennas roughly of 30 something, 38, 30, from 35 to 39 dBs. So we are just very competitive with reflectors. And well, they are manufactured, as I told you. You are on the left part of the slide. You have pics of photographs with photolithography, and also I would like to show you this. That is well, essentially here on the bottom is where you have the radiometer at the laboratory, and in the next slide, this is the design that we were running before the quarantine in our labs from here and in the Rennes University in France for manufacturing the radiometer in the encapsulating of the radiometer. Sorry. So essentially, from 2 or 3 weeks ago, we are stopped, but in theory, if all is working properly in the next month, we are going to have the complete radiometer totally, if you allow me the word, in a monolithic approach, just for being tested as the first proofs. So I don't want to go ahead. I think that is much interesting. If you have questions or doubts, just for being more be directive, if you allow me. I think it's more interesting than you hear the talk, right, SECPHO?
Okay, thank you, Luis Enrique. Is there any question for Luis Enrique? In case you have a question, you can write it down in the chat. You can find the chat in the third icon below, in the third icon starting for the right. Is there any question for Luis Enrique? No. Ignacio Bustamante has one question. Please, Ignacio. Let's wait. Who are the partners of the consortium of Martin Lara, Luis Enrique?
Yeah, this is a regional consortium. So there are two kinds of partners. One that they have already funded, they are funded, and the ones that they are not funded. So essentially, companies are not funded in this consortium, and companies are CENER and Airbus. The partners that are funded, all of them are from the Madrid, Comunidad de Madrid, or Madrid region, public research institutions. From the aerospace point of view, is IDR, the Polytechnic University, together with the Carlos III University. From the electrical engineering point of view, we are the leaders of the project and also the partners for designing the radiometer. From the scientific point of view, is the Complutense University, that is not the physics university, but the maths university. If you want, I can provide you the names of the leaders, just for being sure that you know them. And also, we were in touch with the Astrophysics Institute in Canary Islands. Obviously, they can't be funded, but they were interested in our designs. Also, in parallel to the Martin Lara project, we have a lot of, at least 3 projects with CENER, a company, where they are already funding our radiometers for designing. For example, we have a very huge project with the Fundación CENER for designing radiometers for their satellites and for other biomedical applications, together with security applications. So essentially, they would like to use our radiometers for security, biomedical, together with the CubeSats or satellites application.
Okay. Any other question for Luis Enrique? Jay Corbera, he says, I don't understand, according to title of presentation, which will be the atmospheric or climate parameters to be evaluated.
So I think I mentioned, but probably very, very fast. From the atmospheric point of view, there are 2 scientific applications. One is measuring the water lines in the atmosphere, that is the Airbus one, for checking the climate change conditions. So we are going to map the Earth with a polar orbit. That will be the application for Airbus. And the second one is detecting dust particles in the South Pole, where the Complutense University has a project. Essentially, they extract information about the polarization of the dust particles in the South Pole, and they relate such polarization with the movement of the North Pole.
Okay. Thank you, Luis Enrique. Any other question? Marc de Gagné from Newtech. What is your website address?
Yes, we had a website address before the quarantine, and they promised me that they are going to launch the website by the end of this week.
Okay,
so if you want, I can provide, to Sergio Sáenz the website, and he can spread around.
Well, you can write it here in the chat directly, and everyone will have the access directly.
I can't because
okay.
because okay. they are changing the title of the website. That is the point.
Then when I receive it from you, I will share it with all the participants. Okay. Thank you, Luis Enrique. Thank you very much. And time is over. Then let's go with the next presentation.